Hi everyone. I know it's been a while. It's just been quite busy. Happy New Year. So in this week we are trying to study a paper S2 Transformer for mass-aware hyperspectral image reconstruction by Jiamin Wang, Kunpeng Li, Yuren Zhang, Xing Yuan. This paper actually I learned a lot from this paper. I will talk about them. Um, as you know, I mean, recently there are lots of transformer papers, and it wouldn't be difficult to, or you wouldn't be surprised if, I mean, for researchers to advance to or try transformers for hyperspectral image reconstruction. Um, it's just a natural direction because if you look at the CV community, one of the tasks would be to reconstruct images, and um, and this task share the similar natural uh, I mean, there's similar natural similarity with the most recent advance in image reconstruction from CV. So, oh, in the first part, I'm trying to just highlight the contribution of from this paper. If you read through it, is you can actually also learn the history of the CASSI, which is very interesting. So we see they share many commonalities of methodologies with civic communities. And so in the first part, I would just mainly focus on the main contribution. In later, we can also go through the paper again. So, okay, before that, let's have look at it. So let's have some very brief introduction to the background. So what is hyperspectral images, or in short, HSI? It records the visual similarity. Oh, sorry, it records the visual information upon long-range distributed spectral wavelengths. Okay, what does that mean? Well, so conventionally, and most commonly, a color image is decoded by only 3 channels RGB. So let me take, and if you look at here, or any images in your phone in the conventional civic communities when they deal with color images, or even in large data set such as ImageNet, Stifler and so forth, they are all in 3 channels RGB. So if you look at the wavelength, the spectrum here, so in the visible light spectrum, the wavelength ranges from 400 to 700 nanometers. And so blue lights here 460, green is 430, red is 655. If we want to represent a color image, then it would be efficient to use only blue, green, and red, and we can use some combination of blue of the primary color, so they are they're additive, meaning that we can add blue, some weighted blue, green, and red so that to form any other color. So it's like for yellow color. I mean, this is just basic knowledge of color. So for yellow, we have some weighted sum of green and red, and then we can combine. We can produce a yellow color, and if we want some sign, we can combine blue and green to get sign. And we can actually have three if we add some let's see. So in RGB, we usually have encode. If you programmer, if you coder, you know that you can have some RGB value to represent a color, and there's some weight for each channel. So now the difference between the conventional color encoding and this one is that, well, this one has the long range distributed spectrum, meaning that now we instead of just having three channels, instead of having only blue, green, and red, we have a wide range of colors in different frequencies, in different wavelengths. So in this data set, they have actually 28. So we have 28 different colors with different wavelengths. So that's the basic knowledge. And then for hyperspectral image acquisition, one of the most popular systems is the coded aperture snapshot compressor imager, or CASSI in short. It operates as an optical encoder which compresses the hyperspectral signals into 2D measurements and requires a software decoder for the signal retrieval. So here's the main point. What we should know here is that it's just the software for retrieval. And if you think of it, well, basically, yes, you're correct. Basically, in a nutshell, main test for this paper is, I mean, for this type of system as an from a machine learning perspective, or from CV students or CV researchers perspective, this is a task of reconstruction. So we are trying to reconstruct something, and that's the main thing. And this is and so here we actually have lots of actually have lots of different models now, mainly using deep learning to do the reconstruction. Okay, so having introduced these two basic this background. Before I dive into the details of this paper, I need to talk about this CASI pipeline, which is the fundamentals to understand this paper. So here we have the pipeline can be summarized in two steps. The first step, so we have a cube, 30 cube, specifically in 2D. You can imagine this is in 2D there's image, some kind of image where so we have U and V. So each let's put it here. So each image is actually it consists of the visual information for a particular light range frequency representing some one kind of wavelength. If you go back to the spectrum previously I showed, it represents one kind of color. One, if you think of a conventional RGB, this is one channel here. And in this, so here it is cool because we have many different wavelengths. So here the second wavelength slightly different from here. And here in this figure so we can see starting from red and then orange and then up into some this is I think it's mainly for visualization. So basically a third dimension would be lambda representing wavelength. So now we have and then here we have a mask encoding. This is the in this Python, what it means is that let me go to so mathematically speaking, F is the cube in height width, and n lambda dimension. This is the hyperspectral cube. So we have specifically in the data set in this paper they have 28 wavelength. So in RGB we have only 3, right? So they have 28. Okay, and mask is physical coded aperture. Since we deal with software, we deal with algorithms. We can go to some paper to understand the physical code. But now what we should know is a mask, meaning that if we go through, so here denotes so here is the so here is the pixel wise multiplication, and here is a 2D, also the same dimension, width and height. So basically we have it means that for some pixel, if this is binary mask, it means that for some pixel we want to retain or we want to lose, you want to discard the information in this specific location in this UV represented by mask, or if this so that would be binary mask. It has only value of 0 or 1, whether you want to retain or want to discard the visual information in a specific pixel location. Or if it is a, let's say, some noise or kind of soft mask, it can range from 0 to 1. So it's like 0.1, 0.2, meaning that we can retain it's some weighted visual information from the location. So this is the first stage, and the second stage is the entangling. Let's go to okay, so I forgot to mention that, and because of this because of the mask, it introduces the first challenge, which is the mask stage loss. So we have some loss because of mask. So the second one would be the entangling. Second stage would be entangling and addition. And specifically, it's mainly some shift in y direction. The paper is that y direction. It looks like in the width dimension here is the y direction is dimension in paper. So what it means, so it is that let's see. So intuitively, we want, like here we have n lambda. Eventually, in the end, we actually have only this one. It's actually in one dimension. So here we have h width, and eventually we got the measurement y here. The last one is actually one dimension. It's actually a 2D image. With so then for each pixel is actually sum of the all the visual information across over all the different lambda. But however, it is before that there's before the addition there's an entangling. The entangling is some shift, so in y direction. So meaning that so here lambda star is the reference. So is a predefined wavelength as the anchor, and so lambda is the current wavelength, and then for some specific location in y direction, then let's see here is the y. I know it's kind of intuitive to xy, but here let's say here is the y direction. So here let's say here is the lambda, and here is the lambda star. So it means that in let's say here is the so the U and V in these 2 points in this point and this point are not the same. This in this specific here, there's some shift, some shift in this direction with respect to this point, and which is defined by the function of d here, so that the v is added by some shifting values here. Okay, and then because so after some shifting in y, and also we sum across all these different wavelengths, then we can obtain this measurement y. Okay, so here so entangling means here here or here, and addition means the, so here we for each across all the wavelengths, and we sum all of these f prime is from is the output from the first stage, which is the mask coded cube, and plus some noise denoted as sigma. Noise, basically this is a noise term. You could, a typical one with Gaussian noise. Okay, and let me clear. Because of these, it introduces the second challenge, which is the entangled data loss. So one of the properties, one important properties is the spatial correlation. This spatial correlation vary from adjacent wavelengths. So like here in the neighbor of A, which is in the green area, there's two wavelengths here, and you can see here they are correlated spatial. Spatial means in the UV space, and for this red color, so some orange, some red, for different wavelengths, we see. I mean, they're also correlated, right? In region one, so these two look very different, but these two look very similar. And this is the spatial. Spectral correlation. So basically means that in nearby wavelengths, they're more the information are more, the signals are more correlated in nearby wavelengths. So I think this is how we should read this dimension, so that you see in some nearby, we see some high values here in near. Okay, having introduced this, then let's go back. Let's go to the paper. So summary logic as the contributions for entangled data loss, they use N² transformer. Transformer now is a very good choice for learning some dependency, some long-range dependency, and they also use in order to tackle the second challenge, which includes mass data loss. They introduce mass-aware learning strategies. Compared with L1 and L2, which is a very typical one, but treats each pixel equally. And this is the main architecture for the first one, for the transformer. So first for measure, we have shift and the product and the Y prime and feature extractor. So feature extractor is implemented by layer norm, and it's actually implemented by 3x3 convolution layers, and then we got the feature which is Z in zero stage. Okay, in zero stage features. And then we goes into the S² attention transformer stage. So this is the main thing. In one stage, they have the S² attention block. And then in transformers architecture, they consist of L blocks. So here they have spectral token and spatial token. S² basically represents the MSA for spectral and spatial. So spectral tokens mean before that, let's go to the cube here. So here's the height and width dimension, and third one would be C. C would be the wavelength dimension here. It should be lambda or colors or channel number of channels. So here we actually have 28. Sorry, it's not exactly 28 here because that's the output, because there's the dimension of Z. So it is determined by the number of channels in Z actually here. So here so spectral tokens, we want the unit in representing each wavelength. And to here, and C by C, and so basically, and then spatial. So this one, and then for spectral MSA, from a high level perspective, we want to learn the correlation, the importance matrix. So want to learn the correlation across the spectrum in the wavelength dimension in comparison, or in spatial MSA, we want to learn the correlation in the UV space here. So why it looks like this? So here is the, let's see, so it means that in this, so let's imagine this is height and width. Here, this is a pixel across all the wavelength. Basically, this is the unit, this is a token. So we want to, and here, so basically we want to learn the correlation from this one and across all these pixel locations. And that's the intuition of the why I want to define a spatial token in this way. And for the spectrum, so we have one here. Basically, for each wavelength, we have a 2D map, and we want to understand when to learn this 2D map in how one attempt to or how one 2D map for one specific wavelength attempt to different 2D map across all the wavelengths. And this is the reason why we define the dimension in this way, and this is in order to feed and in order to learn spectral MSA multi-head self-attention there. And after that, we can get the Z, the hidden space, and also put it into a 3x3 convolution. And then there's actually a residue here, you can see from the beginning to the end, so that we can feed so here we got the ZK in K stage, and then go over again. So, and then to produce the prediction, which is the F hat. Okay, now I speak a little bit slowly because I'm trying to make sure I say correct things. Okay, and they try different attention blocks. So the first one is spatial attention. Usually they have the layer norm in the spatial MSA, and with some residual you can see here, and then in the end we have feed forward network. And this one is the spectral, basically replace the spatial MSA with spectral MSA. And then they have sequential spectral and spatial spectral. And third one, they basically want to combine some way to combine spatial and spectral MSA. This one they use concatenation and linear projection layer to combine these two. They call it parallel access attention. Now let's go to the second contribution, which is the mass-aware learning pipeline. I actually learned something from it. It's actually a lot. So actually it follows, it's in the curriculum strategy, machine learning strategy. So curriculum learning, in curriculum meaning, sorry, in curriculum learning, we instead of training the model, everything in the same for across the whole training procedure, they actually increase the difficulty gradually for the training. So it's like at the beginning, so that in conventional, well, in conventional, we could just use like, if you think of reconstruction loss, the first thing you can basically use some L1 loss. Basically you have the prediction denoted as F hat, and then we have the reference which is the ground truth, so that we want to minimize, we want the discrepancy between the prediction and ground truth to be minimal. And then we use L1 norm to define the loss. So in traditional machine learning, you can just do it this way, and just with the hope that the network could do the job. Okay, then the new thing in curriculum learning is that now we specifically, or we specifically identify some difficulty, or gradually increase the difficulty at some stage, usually in the later stage, so that in the, I could see that imagine in the loss landscape, it's like in a huge valley, and when we increase the difficulty gradually, we can the loss landscape can better lead the model to a better or a better minimum, which could be closer, or maybe the exact global minimum. Okay. So that's the main background of the main basic knowledge of curriculum learning that we should know here. And specifically, what that means that, well, at the beginning, so they introduced mass aware. At the beginning, we just use reconstruction loss, and then we have ME, which is mass encoding loss. So here, instead of the end prediction, so this one is the end prediction over lots of blocks and stage. Now we can actually, so here is the K stage defined by ME in the Z, in the feature embedding represented in Z, and then we could have some feed forward function of FH, and then we are trying, so in this, so here we can see the intuition is that we want some hidden layers, we want some feature embeddings to be close to the coded measurement in between instead of the end prediction. Okay, and last one would be the mass aware. Um, so this one is the reconstruction loss, and here MA is that, well, with so here we could see, so here it represents so if some pixel is close to the coded measurement, then it should be close to 0. If not, there's some value. If the value is, if we have some value, it means that we can use this one to represent the difficulty for. It's like we have a we can get for each pixel we can get the difficulty of reconstruction here. That's the main thing. Okay, I hope that I can explain clearly. So let's go to some more details. So in mass aware loss, so here basically we have alpha to control the weight is between ME and reconstruction loss. And this one is implement F of FH is implemented by a Linear convolution structure. And then LMA is the weighted sum. So mass aware loss is the sum of LME plus LMA. So let's go to MA because I guess there's some confusion. Let's go to MA. It means so now let's look at the physical perspective. So mass encoding procedure use the spatial data loss. If you go back to here, we have some mass encoding and we have some mass data loss here because of the mass. Okay, then the corresponding pixel should be predicted with higher uncertainty because it is mass. While the unmasked regions potentially allow an easier retrieval with higher confidence. So basically, for the pixels for the unmasked regions, since we have reference with ground truth, we should be able to easier retrieve compared to the masked pixels. And here's an illustration. So F is the reference and B is the so F hat is the prediction. Minus F means the reconstruct difficulty. And F prime is the estimation of coded signal with mass encoding nodes. So this does basically means the this is the evidence of the masked data uncertainty. Okay, so with this transformer and with this loss, that's the main contribution of this paper. If we go to this paper, okay, then there are lots of visual analysis and so forth. You can read them. Okay, I think I've introduced the main I've already summarized the contribution. Thank you for listening, and let me try to produce another paper next week. And have a great weekend.